heterogeneous equilibrium. The concentrations of gases and solutions are variable and can easily be changed. For gases, changing the pressure or the amount of gas will change the concentration. For solutions, changing the volume of the solution or the amount of solute will change the concentration. However, pure solids and liquids have constant concentrations. The concentration of any pure substance can be found by dividing the number of moles of the substance by its volume. The number of moles is found by dividing the mass in grams by the molar mass, G/mm. The volume can be found by dividing the mass of the substance in grams by the density of the substance, G/d. To simplify the expression, we multiply the numerator by the reciprocal of the denominator, leaving the density divided by the molar mass, d/mm. The density of a pure solid or liquid is constant at a particular temperature. So this means that the concentration of a pure solid or liquid at a particular temperature can be found by dividing one constant, the density, by another, the molar mass. Therefore, the concentration of a pure solid or liquid is constant. So what is the effect of this on the equilibrium expression? Since the concentration of any pure solid or liquid will be a constant, rather than having that constant in with the concentrations that can change, we make it part of the equilibrium constant K. The concentrations of solids and liquids do not appear in the equilibrium expression. For example, let's look at the equilibrium for the dissolving of lead-2 chloride. PbCl2 solid in equilibrium with Pb2 plus ions and 2 chloride ions. The equilibrium expression would be written K sub C equals concentration of Pb2 plus times the concentration of Cl minus squared over the concentration of PbCl2 solid. However, since we know that the concentration of the solid is a constant, we can move it to the same side as Kc, making another constant which we call Ksp. Knowing the solid and liquid concentrations will become part of the equilibrium constant allows us to ignore them when we write the equilibrium expression. Remember, however, that they have been taken into account and are part of K. Here is another example. In the equilibrium for the decomposition of calcium carbonate solid, CaCO3, to form calcium oxide solid, CaO, and carbon dioxide gas, the equilibrium expression involves only CO2, since both solids have become part of K. As long as there is some of both solids present, the amount of CO2 will be the same. Let's look at some heterogeneous equilibria and see if we can come up with the equilibrium expressions without going through the rearranging of the equations. A. SnO2 solid plus 2CO gas in equilibrium with Sn solid plus 2CO2 gas. The equilibrium expression is K equals the concentration of CO2 squared divided by the concentration of CO squared, leaving out both solids. B. 2Hg liquid plus O2 gas in equilibrium with 2HgO solid. The equilibrium expression is K equals 1 over the concentration of O2. Be careful with the math here. When all substances on one side of the equation are taken into K, we must replace the concentrations with a 1. When it is the products that disappear, that leaves us with a 1 in the numerator. C. Zn solid plus Cu2 plus aqueous in equilibrium with Cu solid plus Zn2 plus aqueous. And the equilibrium expression is K equals the concentration of Zn2 plus over the concentration of Cu2 plus. We can write an equilibrium reaction as either the forward or reverse reaction. This creates some interesting relationships that arise from manipulating the reaction. For example, with the N2O4 decomposition equilibrium, the equilibrium expression is K sub C equals a concentration of NO2 squared divided by the concentration of N2O4. Here, the value of K is also given. If we reverse the reaction, then the substances that were the reactants become the products, and the substances that were the products become the reactants. This inverts the mass action expression, and the value of K for the reversed reaction is the reciprocal of the value of the original reaction, which in this case becomes 4.72. If we change the coefficients, this changes the exponents in the mass action expression. If the coefficients are doubled, for example, the reaction still has to be balanced, then all of the exponents are doubled, which means that the mass action expression value is squared, and the value of the equilibrium constant would be squared. A more complicated but equally important relationship comes when we find a reaction as the sum of two or more reactions. The mass action expression of the net equation is the product of the mass action expressions of the added reactions. Any substance that does not appear in the net equation must appear in the reactants in one reaction and the products in another. This would place the concentration in the numerator of one mass action expression and in the denominator of another, where it would cancel out. All that remains in the product is what remains in the net equation. This last relationship is the reason that the equilibrium expression does not depend on the mechanism of the reaction. Since the steps of the mechanism add to give the overall reaction, if each of the steps of the mechanism is in equilibrium, then the equilibrium expression is the product of all the equilibrium expressions for the individual steps, and all those substances that appear in the reactants in one step and products in another, the intermediates and catalysts if present, will cancel out.